and thanks for the organizers. It's a very great pleasure to come here for my first time in IAS. So the purpose of this talk is to present not really a theorem, but more a question I was not able to solve. So maybe it's kind of exorcism for me to explain that question I have been working on for maybe 2 years, and try to show you how it works, why it is interesting, but I do not have the answer. So maybe better like that. And my talk will be in 4 parts, I hope. Maybe the 2 last one will be short. And the first one, I would like to review what kind of review of structures on character varieties. What kind of differential geometry one can find natural differential objects which are defined on character varieties. Will be kind of introduction of the basic objects I will use in my second part, which I will explain what is the derived skin module. So hopefully it derived is not related to derived algebraic geometry. It's much more simple object. And then after that, I will talk about motivations. And this is really standard character varieties stuff. But all the questions I'm talking about come from quantum topology, indeed. So motivations from TQFT or quantum topology and Jones polynomials, etc. But I don't want to spend too much time on this third part because it's really motivation and you can formulate a question independently. And next, if I have time, I would like to talk about an idea which may solve the problem, but I don't know how to work it. It's called twisted intersection. And some ideas around this question I will ask. So let me start with this review of structures and character varieties. So in my purpose, I will just talk about character varieties of surfaces or 3 manifolds. So let M be either a surface or a 3 manifold, maybe with boundary. So the character variety has already been introduced by Mark Keller this morning, but let me just remind you that x of m, I will try to use the same notation, is a set of all representation of pi1 of m into SL2C divided with 2 slashes by SL2C. This is the algebraic quotient, and this is an affine variety. But I have to say, when I will define exactly this variety, you will see that it's not reduced. It's indeed a scheme. Okay, so indeed a scheme, and I will say some words about that in 10 minutes, maybe. But you can, for the moment, just think of it as a usual algebraic variety, maybe with singularities, and whose points are just given by representations up to some equivalence relations. So points of x of m are exactly representation rho from pi1 of m to SL2C, this hopefully. But the relation is just little more than conjugation. So rho and rho prime are equivalent if and only if they have the same traces. The trace of rho of gamma is equal to the trace of rho prime of gamma for any gamma in pi1 of m. So it's known that doing such an identification, you have really an algebraic variety, an affine algebraic variety, and you even have some very natural functions on this, which are just given by the trace because of this obvious definition. So you have f gamma from x of m to c. It's a map which sends rho to the trace of rho of gamma, and this is a regular map. And indeed, I will define indeed the character variety from this trace function. So this is called the trace function. So my purpose here is to explain you that for a specific pi1, which are surfaces or three manifolds, there are some natural objects on the character variety. And the most celebrated one maybe is a Goldman bracket or the symplectic structure. So the first structure is a symplectic structure which is defined on x of sigma for any surface sigma. So maybe the easiest way to define the symplectic structure is to talk about the Poisson bracket. So let me give the formula. So it's a formula due to Goldman. Goldman formula, so it's equivalent to give the symplectic form or to give this formula for the bracket of two functions. So the formula is the following. It's very, very beautiful. So if you compute the Goldman bracket of two trace functions, and let me put 1/2 here just for normalizations, is a sum, just by definition, over all intersection points of gamma and delta. So if your two curves here intersect in some point P, you can compute the sign of intersection. So it's the sum of the sign of intersections. And here I can construct two other possible elements of the pi1. I can just compose gamma and delta followed by P. So this is just, first I do gamma and then delta. So this is gamma union delta. And I can do the opposite way. So gamma first and then delta inverse. And I make the difference here of the trace functions. Okay? So it's a very simple formula like that. And the point is that this defines a symplectic structure, the Poisson bracket. So it's very combinatorial in some sense. Sorry, sigma is a closed surface. Indeed, well, for this Poisson structure to correspond to a symplectic structure, it has to be compact. If not, it's just a Poisson structure. Okay, it's always a Poisson structure, Poisson algebra.
So the Poisson structure is defined even at the singularity?
Yes, yes, it's really an algebraic one. The Poisson bracket of trace functions are trace functions. So
this is a bracket on these algebraic functions.
Yes.
Is it given a natural way of Poisson structure and smooth structure?
On the regular part, yes, it does. Because the trace functions generate the algebra of functions on the character variety. So indeed, I will give little more details in a minute. But this maybe you.
Is it easy to see it's independent of the representative of gamma and delta?
It can be checked by hand, but yes, it's not difficult. It's not difficult. Well, you will see a different way to prove that it's well defined. But maybe many people already heard about this Poisson structure and this, well, famous and invariant by everything. So in particular, it's invariant by the mapping class group mod of sigma. So it's an invariant symplectic structure, and it has a lot of interesting applications. And let me skip to another one, which is which is not as well known as this Poisson structure, and which concerns three manifolds at time. So the second structure is, I would like to show you that once you take a manifold, three manifold, which is not too badly behaved, then there is a natural volume form on the character variety. So construct a volume form on the character variety of M for M well behaved, and I don't have time to explain all the details of this well behaved, but let me, this is known for specialists as the Ride-Master torsion. But instead of giving you the definition of the Ride-Master torsion, which is very, very technical and long, etc., and we do not finally see what it means, let me try to give you a way to construct the right master torsion from simple objects. So a way to construct this form. So there is one simple case and one simple three manifold where I can write down everything. It's the case of a handle body. So fix Hg, a handle body of genus J. Then what is the character variety of Hg? So what is the pi1 of Hg? Pi1 of Hg is just a free group with G generators. So the set of representations is very easy to write down. The homomorphisms from Fg to SL2C is just SL2C to the G. So fix G matrices. But this is a Lie group, so it has a Haar measure. Okay, so here is a Haar measure. So let mu be the Haar measure on that space. But I don't think about it like a measure. I think as a volume form, a complex volume form. And my definition here of the torsion, so the torsion here on the character variety of Hg is the push forward of this measure. So it's just the image of the Haar measure quotient by the conjugation. So this push forward may sound very strange. Let me explain what I mean by this push forward. Here you have, let me make a picture. This is the set of all representation. And this is just the quotient by conjugation. So I have here the Haar measure inside, and I have here the orbits of SL2C acting by conjugation. So the character variety is just a quotient. So I mean, I can find a slice here, and this slice is exactly the character variety. So I have a measure, I have a volume form on the slice because it's given by the Lie algebra of SL2C, which has natural volume, and I have a volume in the total space because the total space is also a Lie group. So I quotient a Lie group by another Lie group, then in the quotient I can make a volume form just here. So this is the right master torsion, which is called T in all my talk. And another remark I would like to make is that I never define T unless up to a constant. So I don't want to give you a precise formulas for T. T or 2T are the same, okay? So don't mind about the normalization, which is not important in what I will say. Of course, it can be, I can make a precise normalization, but I don't want you to, I will have better formulas if I forgot about it. More beautiful. Something real?
Yes, so I need to think
No. Holomorphic. It's holomorphic, and I will give you two examples. Okay? So well, there is a simple example which is complicated, and a complicated example which is simple. So the first one is H1. So the pi1 is Z. This should be the simple example. Pi1 of H1 is Z. And the character variety of H1 is very simple. You just have one matrix. The only thing which imports is the trace of this matrix. So you just, here, you take the generator 1, say, and take the trace of row of 1. This is an isomorphism. But if you write your matrix row of X like this one, up to conjugation, you can always find such X such that your representation is like this, if it is semi-simple, but it's not important in this quotient. Then you find the torsion here in the X coordinate. You can do the computation, believe me. You find T equal dx divided by X. It's a very simple formula. But if you really want to write it using these coordinates here, it's slightly more annoying, because let's call t is the trace of rho, which is just x plus x inverse. And then you compute that the torsion t, well, you just derive dt equal dx plus etc. Computation, you find dt divided by square root of t square minus 4. And this looks strange, but finally it is not so strange, because it has a singularity exactly when t is equal to plus or minus 2. And this is quite natural. It's singular for t equal to plus minus 2 when rho is central. For central representations, you find a pole and the square root. So you see that it's not completely holomorphic or rational in some sense. So this is my first example, but it's a nice formula anyway. Yes. Well, I'm cheating a little in that example. Let me skip on that. So the second example is H2, which is very beautiful, because H2 is just the pi1 of H2 is a free group with 2 generators. And it's well known that the trace x of F2 is a very, very nice variety. Once you have a group with 2 generators, to define the representation, you just need to have the trace of the first, the trace of the second, and the trace of the product. So this is, let's call this group the group generated by alpha and beta. And then for any representation, take rho of alpha, trace of rho of beta, and trace of rho of alpha beta. This is an isomorphism we see to the cube here. And this, well, it's a well-known fact. And you can compute the torsion here. Now I do not give you the computation, but what you find is dx, so call this x, y, and z is 3 variables. You find dx, dy, dz. Point. And of course there is a constant here which is 1 for me. Okay? But there is a constant which doesn't matter. So this is a very, very nice formula. I cannot find a simplest one. And for instance, this torsion is a mod of H2 invariant volume form. So it's when you study the action of the mapping class group on the character variety, you have this form which has to be invariant. So you can just check by hand that if you do this map alpha beta goes to alpha beta beta, for instance, this is an automorphism of the free group, then it corresponds to mapping x, y, z to z, because alpha beta, the trace is z, beta is y, and then if I remember, it's something like x square minus yz, no, yz minus x, thank you. And if you compute the Jacobian of this transformation, you will find 1, of course. This is just because it has to preserve this volume form. This is just an example of a transformation which should preserve the sorry? Yes, indeed, the full automorphism of the free group, outer automorphism, acts and preserves this torsion. But now, well, these are nice examples, but they are just examples of very simple 3 manifolds. So let me explain how to deal with the more general examples. So I can explain you one construction, and you can derive this construction in many possible ways, but I cannot give you a full toolbox for defining it. So start from Hg from any manifold, say M, with boundary of M, a surface sigma g with g at least 3. This is just for technical reasons. It's not so important, but for me, it will be here. So what happens? So I would like to relate the character variety of M and the character variety of a manifold, which I construct by adding by gluing a 2 handle to M on the boundary to x of M prime. So what is M prime? M prime is obtained by adding a two handle to M along some curve gamma inside the boundary of M. So I have my handle body here, or some more complicated three manifold, and I choose a simple curve on the boundary, say gamma here, and I just add a disk along gamma, and I find another manifold. And by Morse theory, every manifold can be constructed just by gluing handles from starting from a handle body. So this is a very general way of constructing. So suppose that I know the Riemann-Master torsion of M. So it's a volume form, character variety of M. And I would like to give you a formula for the character variety of M prime. But M prime, indeed, the pi1 of M prime is simply given by the pi1 of M. You add the disk along gamma, so you kill the curve gamma. So it's just divided by the normal subgroup given by gamma. So it's very simple to understand the character variety of M prime inside the character variety of M. So rho belong to X M prime, which I see that included inside X of M, if and only if rho of gamma is equal to 1. So I can make a picture. This is X of M, and inside I have X of M prime. And here I have the Riemann-Master torsion of T, which is a volume form. I would like to explain you how you can compute the character variety of M prime inside. So first question is, what is a codimension?
Sorry, I mean, you haven't quite had rho of gamma.
Sorry?
You haven't quite had rho of gamma on X. You have trace.
Yeah, but
Why the difference?
it's a normal generator, so you fix one. Well, you take one representant of gamma inside the pi1. And this, of course, will have some importance now. But here so you fix gamma, you fix an element of gamma representing gamma, and the only thing you have to ensure is that rho of gamma is equal to 1 in order to be in X of M prime. So this is a matrix in SL2C, so it's codimension 3. You have one matrix, and you want this matrix to be 1. So this is a codimension 3 manifold, submanifold, generically. So this, of course, there are plenty of counterexamples of that, but let me just give a rough explanation of what happens. And it is included in there is a famous function. There is only one function I defined on the character variety. It's a trace function. So this subvariety is included in the level set of f gamma is equal to 2, as you said. Well, if rho of gamma is 1, the trace is 2. But there is an interesting phenomenon here, is that indeed this level set is a degenerate one. I mean, at this point, the function here is critical. It's a critical point. And even more, you can compute the second derivative as any critical point, and it ranks 3. So you show that. It's very easy, just using twisted cohomology, but I don't explain, that the function f gamma, the second derivative of f gamma at rho, so this is just a usual function. It's a critical point, so I go to the next, has exactly rank 3. So I mean, I can find 3 directions where the derivative here is non-degenerate in these 3 directions. In these 3 directions are exactly the normal bundle of x of m prime inside x of m. So this is what happens in general. And the good point here is that it also gives you a way to define T prime.
So you're saying that this is exactly characterizes the subset?
Yes, yes. A generic point, okay? So indeed, we have, well, you have to think that here we have an equality, even if it's not completely correct, but at the generic point of a well-behaved manifold, this is exactly what happens. So you can really identify this with the level set of f gamma. But more than that, T prime now is obtained by, let me write, by contracting T, so the volume form you have here, with the second derivative, d2 of f gamma. So let me make a precise statement. I will say that precisely. If I take E1, so T prime of E1 En is equal to 1. So if I take here n vectors in the tangent space, I would like to say that the volume of these tangent vectors will be equal to 1 if and only if I add to them an orthonormal basis of the second derivative, I have 1. Which G1, G2, G3 is equal to 1 for G1, G2, G3 orthonormal in a complex sense with respect to the second derivative of f gamma. There are plenty of sign ambiguities. The torsion is really defined up to sign. Global, but it's a global. No, it will not happen. But let me skip this. But globally, of course, there is a big sign ambiguity, and I don't really want to explain how to. So let me give a nice example. So this is a claim that the torsion, you can finally compute it just from the trace function and the ambient function. So it's a recursive way you can define the torsion everywhere. So a nice example is the case of, well, I talked about 3 manifolds, but I just can take a product of sigma cross I, okay? This is a 3 manifold, okay? And this, well, it has a volume form, it has a symplectic form, plus a volume form. Symplectic form because it's a surface, and volume form because it's a 3 manifold. So what are the relations between the two? Well, it's very well known indeed. I think this is due to some famous guy from here. Witten showed that in some paper that the Reidmaster torsion of x of sigma is indeed the Liouville form associated to the symplectic form. So T is just omega to the n divided by n factorial, where n is half the dimension, so it's 3g minus 3. Okay, so there is, of course, a relation between the two, but you can prove it using this trick. So you just start from a free group with 2g generators, okay, and compute the function which is a trace of the commutator. So to rho associates the trace of rho of A1, B1, AG, BG. Okay? And you know that the character variety is just the level set equal to 2 to this function. So you have you can really reprove this formula using this construction. Okay? I reprove the formula. So it's kind of difficult exercise, but you see that everything can be checked from this construction. So let me.
In what we've said so far, when did you use SL2C, or is it true for any?
I don't use really SL2C in that case.
You used it for this different geometric exam?
Yes. Now, for that, for SL2C and for symplectic forms, you don't need SL2C. But now you will. Sorry for the noise. So I hope that you have some idea now of Reidmaster torsion. And I would like to here to present some object which is very famous to people doing quantum topology. So it's my second part about the derived skin module. But first, maybe I have to explain what is a skin module, which is a very nice topological construction, which has been invented for the purpose of defining Jones polynomials. But this is not really my point here. I use it for other purposes. So here's the second part. It's a derived skin module. So let me recall very quickly what is a skin module in general. So fix R a C algebra. C is not necessary, but just for convenience. And T an invertible element in R. So I define the skin module S of M with coefficient in R and specific value T is a R, the formal R module, free R module generated by isotopy classes of banded links, isotopy classes of banded links. I will explain in M. So what is a banded link? Is just a link with a band. So here is an example. Just an embedding of an annulus inside M. Framed. But I prefer to say banded because the knot itself is not oriented. The band is oriented, but not the knot. That's why I say framed. I say banded and not framed. Okay? It's important in my definition, indeed. Up to some local relations, which are very famous, the Kaufman relations. So the first one. So if I have a link which inside the ball looks like that, I call this L cross. I can replace it by this. Let me call this L infinity, or replace it with this one. And I call this L0. And the relation K1, the most fundamental relation, is that the isotopy class of L cross, by definition, I put it equal to T times L infinity plus T inverse times L0. This is the first relation. And the second one, so if I add somewhere in my link a trivial link, then I multiply by minus T2 minus T minus 2 times the class of L. So these are local relations, and well, it takes a lot of time to understand why it makes sense to do that. But let me show, for instance, that in a specific case you can understand that it makes sense. So the first example, so in my talk I will vary R. I will take three different possibilities for R. And the first one is R equal to C, and T a specific element. So first example, I take R equal to C and T equal to minus 1. So it's a very simple case, because in that case, T is equal to T inverse. So in some sense, it doesn't depend on the crossing. So you can just, because of this relation, if you remove here, if you change this crossing, you just exchange L0 and L infinity, and it should be the same. So it really means that in that case, the isotopy class of L doesn't depend on the embedding of L. It depends on L just up to homotopy. So in that case, one consequence is that the skin module of M, C, and minus 1 is an algebra. Just by the following rule, if I have a link L and I multiply by a link K, by just making them disjoint in any possible way and taking the disjoint union. And because this makes the embedding independent of the embedding, this is well defined. This is a commutative algebra. Okay, it's a very simple commutative algebra. And everybody here knows what is this algebra, even not in that way. Okay, it's a very well-known algebra, or almost well-known. Well, the theorem, which is due to Prigi, Ski, Sikora, Bullock, Brumfield, Hilden, and Procesi, is that, well, it's an algebra, but the spec of this algebra, if you allows me to use this word. So it's a Noetherian algebra, finitely generated algebra. So it's an algebra of functions on something, and this something is the character variety. Exactly the one. So for me, it's a definition. For me, okay. I would like to define the character variety as the space such that this algebra is the algebra of functions on it. And let me make just one comment that it's not crazy. So how do you, well, if you take this, to make this precise, I have to say how what function I associate to a curve gamma. And what I will associate is a trace function, but with a sign, okay? It's minus f gamma. And sorry? Yes, here the banding is not important. And a comment that all this person proves in different papers, and well, it's a complicated story to understand who did understand that. But I would like to say that these three people here understand that the module was indeed the same as something which was already studied by these guys. But finally, if you really want to see the proof of this fact, it's here and only here. Okay, it's a paper in '87 of Procesi, which really proves that, well, the relation, what you have to think is that the relation between the trace functions are exactly the relations given here. And this is a famous trace relation, which amounts to say that something you know very well, trace of AB plus trace of AB inverse is equal to trace of A times trace of B. And it's the only important fact you need to know to understand the algebra of invariant functions on the character variety. And this is just a reformulation of this fact. But I think it's nice enough to be stressed. But indeed, you can even use it as a definition. This is what I do. So, okay, I am very late. So let me define. So let me say something more about examples. So in general, let me see. I say for any R, the algebra S of M is not an algebra. For the space S of M RT is not an algebra, because you cannot just take disjoint union. If you do that, it depends on the way you present the knot without crossings, except in one particular case, except for when you can do that in a well-defined way. If you have two links inside the manifold and you can put them disjointly, there is a case when you can do that if M is sigma cross I, cross 0, 1. Okay? Because in that case, you can just define gamma times delta by the same formula, gamma union delta, but this you put it above and this below. And this is well defined. They do not mix themselves, so you have an algebra which is non-commutative. Non-commutative algebra, and this is called the Kaufmann algebra, and it is well studied. So, so maybe this you already heard about that, I don't know, before. But let me now explain something different, what is this derived? Sorry?
Is it commutative for an annulus and disk?
Yes, it's commutative for a sphere with 3 punctures, and that's all, or something smaller. Well, in general, it's not commutative. Yes. It really depends on the way you present M as sigma cross 0, 1. You say that's exactly like this. So let me go to my main topic, is what is a derived skein module. Well, it's a very simple idea. Well, here, if you take R equal to C, you have the algebra functions on the character variety. You have the trace functions. And if you take R equal to C T inverse, you have something which is related to the Jones polynomial. So you can just do something slightly more than C. This is the idea, is to put R to be the dual numbers. Okay? Just try to put this like a ring of coefficients. And T, you just take -1 plus something small. Okay? And this, I would call it S prime of M, by definition, is S of M, R, and T. And this is a derived skin module. And let me try to convince you that it's an interesting thing to look at. So let us look at the case when M is equal to sigma cross 0, 1. So, I forgot to say something about this Kaufman algebra. Let me, yes. In general, there is a very simple construction. If you have a link for any link L inside sigma cross 0, 1, you have a very complicated link inside a secant surface. You can project it down. You can suppose that it has a nice diagram. So project it on sigma. So you have a diagram of inside the surface. And anytime you see a crossing, you can apply your favorite Kaufman relation. And you replace your link with a combination of two other links with one less crossing. Okay? This is equal to T times something plus T inverse times something else. Two other links with one crossing less. And you can just do it by recursion. You can apply the same relation. And finally, there will be no crossing at all. And if you have just one simple curve like that, you remove it by applying the second Kaufman relation. So finally, in general, you have the following very simple elementary statement, is that S of MRT is a free module generated by multicurves. So it's free just because you can decompose it by solving the crossings along the bases, which are curves which have no crossing at all, which I call multicurves. Multicurve is just an embedded submanifold gamma inside sigma, which no component bounding a disk. Okay, so multicurve, by definition, is a embedded one submanifold without trivial components. So this Kaufman algebra is something even more important than being an algebra. It has a basis. It's free. And let me just, for you to understand what I mean, just do a very simple computation in Kaufman algebra. So suppose that M is S1 times 0, 1. And let me make a picture. So this is a torus. And the 0, 1 is just in the sense of the direction of the blackboard. So I can just multiply this curve, say, times this curve here. So by definition, it's just put one above and the other one below. So the product of these two curves is just this union of two curves here. And here you can apply a Kaufman relation. So this, by definition, is equal to T times this plus T times this. Okay? And here maybe you recognize something I was talking about at the beginning of my talk, the Poisson formula. It looks like I'm computing the Poisson bracket of these two trace functions. But of course it's not, because here it's an algebra and the Poisson bracket is not an algebra structure. So the relation, you can express it in terms of this derived skin module. So if you compute S prime of sigma cross 0, 1, this, because using the basis, decomposing along a basis, you can identify it with the skin algebra of sigma, the usual one, tensored by C epsilon divided by epsilon square. Because there is a basis which doesn't depend on the system of coefficients. So indeed, it as a C epsilon over epsilon square module is just completely isomorphic to that, but not as an algebra. Not an algebra isomorphism. I can write down the product of, say, f plus epsilon f prime. So using this decomposition, I can say that an element of this algebra is just the sum of a trace function plus epsilon times another trace function times g plus epsilon times g prime, and compute it. Well, if I just remove this epsilon part, I just find the product of these two. And if I look at the following part, I have the cross f g prime plus f prime g, and I have some Poisson bracket here which appears here. So this is a definition of the Poisson bracket. Indeed, this kind of deformation of the product here in the Kaufmann algebra. But so the motto here for my talk is this derived skin module contains information on these structures, differential structures on character variety. And this is really what I try to explain in my remaining time. So maybe my second and my parts 3 and 4 will be for another time. I'm really out of time. So this motto, at least I have I'm true in the case of surfaces, okay? Because, well, the derived skin module is exactly contains this information, contains the Poisson bracket. But things become much more interesting if you look at 3 manifolds. Okay, so one first goal. Well, in character varieties, well, suppose you have a manifold. Let M be a 3 manifold with boundary sigma, which may or not be connected. Okay, so you have 2 character varieties. You have the character variety of M, and you have the character variety of the boundary. And well, in Mark Kohler talk, it was very clear that one very important thing to understand is the restriction map here. So how does the representation restrict to the boundary? So here is a restriction, so rho, which sends rho to rho divided by sigma. But first I would like to explain what is this map and why it is algebraic map, for instance. But with my definition of skin module, it's completely obvious. Because just look at the dual picture. So to define a regular map from this affine space to this affine space is to define an algebra map from this algebra to this algebra. But here I have sigma, so let me another notation. So Bm, it's a strange boundary of M, is just a neighborhood, a tubular neighborhood of the boundary. Of sigma in M. And obviously it's a secant surface, so everything I was talking about in the case of secant surface applies to Bm. But I can do a very simple map here. If I have a link inside Bm, I can just send it to itself here inside M. Okay? And this is an algebra, just it's completely obvious. And this is exactly the dual of this map here, of the restriction map. And one thing, my first goal, so let me go to my point. Here we have a symplectic variety, and here we have a manifold. I would like to explain that this is indeed a Lagrangian embedding. So show that this map R is So generically, or with some hypothesis, because it's not always true, is a Lagrangian embedding. I mean, for any point, the image of the tangent space is a Lagrangian subspace of the tangent space of X of sigma. And I would like to show you that you can almost derive it from skin modules arguments using this derived skin module. So first, make a general assumption. So my first point is that in the skin module, the derived skin module itself, there is absolutely no information. That's a pity, but let me explain more precisely how the derived skin module is related to the usual skin module. There is two very simple maps between the two. First, if you have some link L inside M, how can you make from it an element of the derived skin module? Well, there is only one way. You just multiply it by epsilon. If you do not multiply by epsilon, this map will not be well defined. Okay, but this is well defined. And on the contrary, if you have an element of the derived skin module, so with coefficient in C of epsilon, you can just put epsilon equal to 0. Okay, so I'll just say take it mod epsilon, and you get again some element in S of M. Oh, sorry, S of M is my notation for the algebra with C and -1. So the algebra of functions on the character varieties, the algebra of trace functions. So the usual algebra everybody knows. Okay. And here I just map L to L. So here I have a very nice complex. Okay, it's a complex because if I compose it's 0. And my first question is to show that it's exact. I do not know any counterexamples. So this is a good news and a bad news at the same time. So if it's always exact, it's fine, because you will see I have some consequences. If it is not, then there are some information here, okay? Because maybe I can say something about the character variety inside the S prime. But I believe it is always exact. So it means that this is just an extension of the two, a trivial one. There is no, algebraically, there is nothing to see inside the skin module. But the interesting thing to look at is, again, this restriction map. Okay, so let me make a commutative diagram. So I have define P to be the kernel of the map here from boundary of M to S of M. So this is by definition the kernel of this map. P is very important for our purposes. P is exactly the algebra of functions on the character variety of the boundary, which vanishes on the character variety of M. So indeed, it's exactly the algebra of functions on the image of the restriction map. So indeed, P is the algebra of functions on the image of X of sigma Zariski closure here. Okay, so you have to think of no, it's the ideal. It's a quotient, which is the ideal of functions. Well, ideal associated to this Y, which by definition is the restriction of the character variety. And my point is to show that I would like to show that this is a Lagrangian subvariety. This Y, which is exactly the projection of the character variety of M inside the character variety of the surface. And one way to show that is to show that at least that if I take two elements of phi, two functions which vanishes on the boundary, and I take the Poisson bracket, I should have 0. So 0 means to be again in the ideal. So this is one statement equivalent, almost equivalent to showing that the restriction map is a Lagrange embedding, is to show that Poisson bracket of P and P is included in P. Okay, so let me explain how we can see it from these derived skin modules. So it is an exercise. You have this here map. You have this P prime here. You can define it the same way. S prime of Bm, S prime of M, and you have this S of M again. So let me just make a big commutative diagram. I know everybody likes commutative diagrams. Etc. So here is just the restriction map and the algebra functions on the boundary. And suppose that, well, it's a very important picture for my purpose. I'm sorry that maybe complicated to follow. And we make the assumption that all the columns are exact. Okay? So suppose that you have exact columns. It's exactly this regularity assumption which I believe is true, and I don't know how to prove. Okay? But it's completely, in some sense, natural. It's just things should be like that. And let me prove that just by assuming that you have exact columns, you have this here. So it's very simple. You take two elements in P here. Okay? So because this is exact here, it means that you can add something with epsilon so that they belong to P prime. So there exists F prime and G prime such that F plus epsilon F prime and G plus epsilon G prime belongs to P prime, just because this is surjective. Now P prime, you have to think about it, but P prime, all these P and P primes are ideals, because if you have something in the boundary which is 0 and you multiply it by something else, it stays 0. So the commutator here is also an element of P prime, just because P prime is an ideal. Left ideal, but it doesn't really matter. But you can compute this precisely because of the formula I wrote here. If you take the commutator, you just get something very simple. You get this equals to epsilon times Fg. Okay? Just direct computation using this formula here. So it means that here it comes from P by multiplication by epsilon. It precisely means that the Poisson bracket of F and G belongs to P. Because, again, of exactness here. Okay? So I hope that I convinced you that this assumption here is somewhat natural in constants, these Poisson structures. And so let me finish. I'm sorry, I need really 5 minutes for giving the question I was interested in. Because this was just the first goal. So my second goal and main goal is really to understand what is new in this picture. What do we learn from character varieties by looking at this kind of skin modules and derived skin modules? And the point, I believe, is that it says something about the right master torsion. Okay? So the second goal is to prove a relation with Reidemeister torsion. So let me explain it very well, how it works. So here I made an argument. I said take F in P, okay, And I said, well, you can find some f prime such that f plus f prime, epsilon f prime is in p prime. But indeed, this f prime is well defined up to the adding some element of p. So an associated f prime, which I call this y of f, such that, well, f plus epsilon f prime belongs to p prime. Okay? So I mean that the question is understand this operator y, which goes from p to, well, elements of the skin algebra of boundary of M. So I mean trace functions on the boundaries up to p divided by p. Okay? And really try to understand what is hidden in that thing. So this is a function which vanishes on y. This is a function vanishing on y. So you have a character variety of sigma and character variety of M, so y, which is the image of the character variety of the 3 manifold. And there is an operator which tells you once you have a function which vanishes on y, gives you a function, because this is the algebra of functions on y. So what it should be, and I believe that we have the following. So the question it's a very strange formula, but prove that u of f is the divergence of the Hamiltonian vector field associated to f with respect to t. So let me write it differently. So you have the torsion is a volume form here. So this is really differential geometry. You have a volume form on y here. And you have a function which vanishes on y. This function on a symplectic variety, a function has a symplectic gradient, a Hamiltonian flow. So it's a vector field. And this vector field has to, because the function vanishes on y, this vector field is a vector field on y. So this is xf. So a function f in P gives a vector field on this subvariety. And I would like to show that if you derivate the torsion with respect to this vector field, you get exactly this guy. So this is a definition. And the divergence is just the derivative of the volume form with respect to a vector field. And there is one natural volume form in that story is T, okay, the Ride-Master torsion. So I'm just let me write it in formulas in coordinates, just to make it more transparent, because this maybe it looks very complicated. In coordinates, you have the following situation locally. You have the character variety of sigma is just, if I take a picture around here, is isomorphic to C to the n. The symplectic form is just dxi dyi. And the Lagrangian is just given by y1 equal yn. So this is C to n equal to 0. And the Ride-Master torsion is just a function a, which depends only on x1, xn. Okay, so it's a function on, this is x of m. So you have a function here, sorry, times dx1, dxn. And if you write down what it means, this, you get that the divergence here is some very simple operator. It's just the derivative mixed dxi dyi plus af divided by a. Okay, some very formula like that. The second order operator. And so for the proof, I know I can give you the list of examples where I'm able to prove it. But indeed, I prove it because I know everything in the computation. So I just prove it by checking. If I know everybody who appears, then it works. So the proof is for sigma cross 0, 1 for handle bodies, and this is yet complicated to show for handle bodies, and for some complement of knots, so complement of torus knots and figure 8. But I would like to stop these examples and to find a good reason for this to hold. Okay, let me stop now.